So, does motion have weight? I mean, it sounds kind of like a trick question, right? But believe it or not, physics says, yeah, it does. The energy of a spinning object actually adds to its mass. So, how in the world can we possibly weigh pure motion? Let's dive in.
Okay, we've all seen it. E equals mc squared. It's probably the most famous equation on the planet. But it's not just for, nuclear physics or distant stars. It tells us something really deep. Energy and mass, they're basically two sides of the same coin. So what does that actually mean for something super simple, like a spinning top?
Right. So this core idea is called mass energy equivalence. And what it means is that any object with energy, and I mean any kind of energy, including the energy it has just from moving, that energy contributes to its total mass. So yeah, a baseball flying through the air is technically infinitesimally heavier than one just sitting on the ground. The big question is, by how much?
Okay, so to get our heads around this, let's use a simple thought experiment. It's based on a classic setup in fluid mechanics. We're going to imagine a spinning bucket of fluid, and we're going to try to figure out the extra mass that comes just from the spinning. So, picture this. You've got this cylinder of fluid spinning like a blender. The thing is, the particles right in the center are barely moving at all, right? But the particles way out at the edge are whipping around at top speed. This is super important because it means the kinetic energy isn't spread out evenly. It actually ramps up dramatically the further you get from the center. Okay, so you've got all of these different speeds and energies all mixed up inside this one spinning thing. How in the world do you calculate the total extra mass? It sounds really complicated, but the process is actually surprisingly straightforward. Here's how the logic works. First, you model the system, our perfect idealized cylinder of fluid. Then, you calculate the total rotational energy. You do that by basically adding up the kinetic energy of every single little particle. And third, you take that grand total of energy and you plug it right into our old friend E's mc squared to find its effective mass. And bam, that gives you the exact amount of mass added purely by the motion. Now, after you do all the math, the calculus of adding up all that energy across the whole cylinder, you'd expect the answer to be some long, messy, complicated formula. But what physicists discovered is an answer that's just incredibly clean, super elegant. It boils this whole complex system down to just a few key things. And here it is. This is the big reveal. This incredibly simple formula tells you exactly how much the mass density increases for our spinning fluid. Let's break down what this actually means. All right, so here's the really cool part. The increase in mass really just depends on two things: how fast the fluid is moving at the very edge, that's the edge, and how that compares to the speed of light, c. And that 1/4 at the front, that's just a little geometric factor that pops out because of the specific cylindrical shape we're using. Okay, so a formula is cool and all, but what does this actually look like in the real world? Let's take this out of the theoretical and imagine we're in a lab. What would happen if we actually tried to measure this thing? And this just perfectly shows the scale we're talking about. If you spin some water at 224 miles per hour, which is pretty fast, its mass would increase by, wait for it, about 3 trillionths of a percent. I mean, that is just an absurdly small number. Yeah, that change is so ridiculously tiny, we don't have a single instrument on Earth sensitive enough to actually detect it. It's a change that for our everyday world really only exists in theory. So you gotta ask, if we can't even measure it, does this idea even matter at all? And the answer is a huge, resounding yes. We just have to look up. Let's scale things up from our little lab experiment to the cosmic level, and you'll see how this tiny effect builds into something that literally shapes our universe. Okay, this is where it gets really wild. Let's compare our lab blender to a spinning neutron star. A neutron star can spin so incredibly fast that its surface is moving at something like 10% of the speed of light. Now, at those kinds of speeds, the added mass from all that rotational energy is not negligible anymore. It's almost 0.25% of the star's total mass. That's huge. And believe me, that extra mass matters a lot. It adds to the star's total gravity, which changes how it pulls on everything around it. It even affects the star's internal structure, its very stability. So this hitting mass from motion, it's actually a critical piece of the puzzle for understanding the most extreme objects in the cosmos. All right, so let's wrap this up. What are the big takeaways here? First, all energy has mass, even the energy from something just spinning around. Second, we have this beautifully simple formula to calculate it. Third, while the effect is basically zero in our daily lives, it becomes a major player for things moving at relativistic speeds, really shaping how our universe works on the grandest scales.
And all this leaves us with a really fascinating final thought. We've just seen how simple rotation adds this little bit of hidden mass to everything that spins. So it makes you wonder, what other forms of energy, like heat or the energy in chemical bonds or even pressure, what are they all contributing, little by little, to the total mass of our entire universe?